Hey guys, we're moving into our next chapter, which is primarily new. You can see on the front page here, it's a lot longer than these last two little mini ones we did. So this chapter 2 test will be a 100-pointer, where the last two haven't been. This is a far bigger content of new material. So we're going to revisit our old integration techniques, primarily use substitution, but this mega integration worksheet number 2 is just working out all kinks in integration that hopefully you got 90% down. And I'm going to revisit the inverse trig functions because, to be honest, last year was so goofy at the end of the year. I feel like I covered it for a day, but I knew it wasn't going to be on the AP exam, so I don't think we delved into it much. But it's definitely a BC topic, so I mean, it'll definitely be tested on the BC test. It's a B topic, but so we're going to integrate where our resulting antiderivative is an inverse trig function, arctan, arcsine, that kind of thing. And as usual, in order to be able to understand integration, the derivation has to come first because they're inverses. So although our end game today is to be able to take derivatives integrals that result in inverse trig functions, in order to do that, we need to first work with or revisit the derivatives. So maybe you remember these because you remember memorizing them last year. I told you you needed to memorize the derivative of arcsine and the derivative of arctan. I gave you a little way to do it. I said, you feel prettier when you have a tan, and that might trigger it for you. But I'm going to derive them just because it's really good math. So suppose I'm going to do arctan first, to be honest. So suppose my function is arctan u. So I'm doing dy dx. I'm going to take the derivative. I don't know the derivative of arctan. I only know the derivative of tangent. I know it's secant squared. So the first thing I do is I'm going to get rid of the inverse trig part of it and just go to trig. So to undo arctangent, you tangent both sides. The tangent of tangent inverse, right, undoes it. So the tangent of arctan u is just u. It's like squaring a square root. So the argument on tangent is y, which means the angle in question, because remember tangent's all about SOHCAHTOA, and in particular TOA. So if the tangent of the angle is u, or u over 1, TOA is opposite over adjacent. So it'd be u over 1. And then the hypotenuse would be the square root of a squared plus b squared. So if I go Pythagorean on you over there, then what I'll do is say, well, I do now know how to take the derivative of tangent y, and I'll take the derivative of u, or du dx. The derivative of tangent x is secant squared x dx dx, or just secant squared x. The derivative of tangent y is secant squared y times dy dx. Du dx, we usually just call u prime. You can call it du dx if you want, but I'm going to leave it as u prime if you don't mind. So remember, my goal is to figure out what is the derivative of the arctan of u. And that's what y was. So my derivative as a function of x will be u prime, the derivative of u, over secant squared y. So I'll go back to my right triangle and do secant squared. Well, secant is 1 over cosine, right? Cosine is or adjacent over hypotenuse. So I need to do hypotenuse over adjacent, right, for secant. So I do hypotenuse over adjacent, hypotenuse over adjacent, but then I square it. So I will be getting u prime over 1 plus u squared. And if you remember last year, I said all of these have a u prime on the top. We could derive all 6 of them, but you're always going to get a u prime on the top. So let's go make a list here. Now, the only thing that happens with the cofunctions, and we could prove it, I could do the same argument up above with cotangent, but the only change that there would be, you can try it if you don't believe me, is you end up getting a negative u prime. We did it last year, over 1 plus u squared. So the cofunctions really don't require any more memorizing. It's just like this, cosines is the same as sines, always has u prime on the top of it, right? Just negative. Same with the derivative. It's a lot of writing here. Of cosecant u is still a u prime on the top, but it's negative. So you'll notice last year I said, these aren't really so bad to memorize. To be honest, AP only covers these, and I wouldn't put it past them to maybe have one cofunction and have it be that, but I have never seen the other ones. So you're going to see your worksheets going to focus mainly on these three, and in particular these two. But it doesn't mean I'm cutting out the hard stuff. The other ones are the same thing. It's just more to memorize. So, but to keep the memorization down, u prime on all of them. Last year we said tangent was nice for two reasons. It didn't have a root like sine does, because we memorize sines. Sine had a root, and we'll derive it just so you can believe me, but they all have u prime on the top. Cofunctions all have negative u prime. And we said it's uglier for two reasons. And again, you feel like you're pretty when you have a tan. It's prettier. It doesn't have the root. And then you'll remember I said, and the subtraction makes this one a little uglier. So sines is u prime over the square root of 1 minus u squared. Cosines is negative u prime over the square root of 1 minus u squared. So you notice I kind of get 2 for 1 on all of these. I don't think I'm going to do the secant one just for time purposes. I am, though, just to keep it real here. I will derive that one for sine. But remember, the derivative of the inverse trig functions always have u prime on the top, right? 1 plus for tangent because it's prettier, square root and a minus for sine. Okay, cofunctions always go negative. You don't really need to know secant or cosecants. We could figure them out if we had to, just the way that I'm going to do arcsine. So let's let y equal arcsine u. If I'm not lying to you, when I derive it, we'll get this sucker right here. Okay? So I don't know the derivative of arcsine, but I know the derivative of sine. So understand the madness, right? Why am I doing this? It seems silly. No, I don't know the derivative of arcsine, so I'm just going to sine both sides to get rid of it. And sine of arcsine undoes it. So again, my angle, the argument in the sine command is y. Sine is opposite over hypotenuse. So we'll have the u here and the 1 here, because it's just u or u over 1, which leaves this one as the square root of c squared minus b squared or whatever. That's just Pythagorean. A squared plus b squared equals c squared. All right, so back over here. Now I'll take the derivative. Why? Because I know what it is. The derivative of sine y would be equal to the derivative of u, or du dx, or u prime. That always happens over there, which is why they always have the u prime on the top. Now, when I do the derivative of sine x, I get cosine x dx dx. When I do the derivative of sine y, I get cosine y dy dx. So don't forget, that's like a little chain rule reaction going on there. So my dy dx, and you can see why the cofunctions go negative, because had that been cosine, its derivative is negative sine. So when I divide, you can understand why all those cofunctions end up just being the opposite of the original, just due to SIGN S's, right? So my derivative of y, and remember y as I defined it up there, was arcsine u, right? It's kind of cool stuff. I love this type of math. I love knowing why stuff is the way it is. If you don't, you're just going to have to humor me because you're going to see a lot of it this year. So here's u prime, the derivative of u. Now I'll go back up to my right triangle and do cosine of y. Cosine is adjacent, root 1 minus u squared, over hypotenuse, which is 1. So you'll notice it was uglier for two reasons. It did have a root and a minus. maybe I'll make that extra credit. If you're listening to these notes and you do the one for Arc-Secant, send it to me and I'll give you some extra credit. So we're going to leave that one undone. Not because it's hard, it's all the same stuff. So again, here's my u prime. My sine's the uglier one. Cosine just goes negative, and these three are the ones that I will hold you responsible for committing to memory. Now those are derivatives, but if the derivative of arcsine u or sine inverse u is this, then the integral of that better be arcsine. Okay? So down here, you'll notice that when we have this uglier one, it doesn't have to be a 1. It can be an a squared minus u squared. If I could do the proof of this, which I can't do until we cover something else, you're just going to have to trust me for now, but we will eventually prove that. But just kind of remember the uglier one that looks Pythagorean, and again, it's uglier for two reasons. The root and the subtraction goes to arcsine. And the way I tell kids to remember this, it sounds dumb, but think of U and A as urine analysis. Okay? So this guy goes to arcsine urine analysis. Here's what I mean. If you had 1 over the square root of 9 minus x squared dx. This looks Pythagorean-y. U sub does not work. The derivative of the inside function is negative 2x. That's not living in the integrand anywhere. I feel like I'm a little bit stuck, but this looks, what we're going to be saying, inverse Triggy. It looks like there's something squared. A would be a 3. It looks like there's a function squared. U would be x, right? Du is dx. So I end up getting arcsine u over a. Now for tangent, it's almost the same thing. Remember, tangent's prettier. It still looks Pythagorean-y. You still have those perfect squares being added. There's no root, but it's 1 over analysis, arctan urine analysis. Okay, so had this one had the root off of it, and you're going, hey, u sub doesn't work, but it looks a little Pythagorean. Like, I mean, things are being squared and added in the denominator. It looks a little arctan-y because it's prettier. Had there been a negative, it would look a little bit arc-cotan-y, right? So, anyway, this one is, A is 9, 1 over A, I'm sorry, A is 3, arctan urine analysis plus Carl. Now, if it were all that easy, I don't have to talk anymore. So it does get a little harder, but here's your algorithm. The first thing you need to do is ask yourself, does it look Pythagorean? Could it go arc-triggy? I'm kind of making up words here, but that's really what you do. You always go for u sub, but when it doesn't work, now that's what this chapter's about. If it doesn't work, it being u sub, I need another technique. And sometimes they're set up for this inverse trig antiderivative. So first of all, you have to identify what's A. Okay, is it something being squared? Yes. A is 1, A is 2, A is 1. We'll do 3 real easy ones here first. Then you need to identify U, something that's being squared. U is X, U is X. That's the best case scenario. When U is an X, there's a little twist to it. Okay? And then you have to make sure that you generate, and this is the most important part, dx. But on this one, my du dx is just 1, or my du is 1 dx, so they're the same. Same thing over here, du dx is 1, or du is just dx. Same thing over here, du dx is 1, or du is just dx. So there wasn't really much to generate. There was no need for what I call a fraction correction. So this is purely arcsine, because it's uglier, urine analysis, u over a. This is arcsine, and don't forget Carl, x at its most basic form. That's it. I call it a naked arcsine. This right here, also the uglier one, for 2 reasons. The root and the subtraction. It's arcsine, urine analysis, plus Carl. So once you identify them, it seems pretty easy. This is what I would call naked arctan. It's 1 over analysis, which is just 1 over 1, But had this been a 25, it'd be a 1 over 5. So, but this is a naked one. It's 1 over analysis, 1 over 1, arctan, urine, analysis. So this is just arctan x in its most naked form plus Caro. Okay, so these three were really easy. Now what happens is when I mess with them, and when they look Pythagorean-y, but they're not. All right, so right up here, again, we always go to u sub first. I don't like the dx on the top. You might say, why do you put it there? Because I want you to get used to seeing things in all of their forms, not just the form that LaRue likes it in. All right, but I don't like it like that, so I like to write it like this and disengage the dx from the argument in there. Because really, if you remember, these are bases and heights of rectangles, and when it's dx over that, it doesn't look like it. But the dx is the width of the rectangle. You're still finding an antiderivative, and if I had numbers here, I'm still finding the area, right? So I'm going to try u sub in my head. U, let it be the inside function. du is negative 4x dx. I don't have any x living in the integram, so my u sub fails me. But it looks a little what I would call arcsine. There is an a that's being squared, right? It'd be the square root of 5. Now what I have is 1 over the square root of, I do have a squared right there, so that's fine. There is something being squared. It's square root of 2 times x that's being squared. So that's minus u squared. Be careful with this. My du dx is root x. Root 2, sorry. So my du is root 2 dx. So when I generate this dx right here, right? I meant to use a highlighter. When I generate that dx, this is what most kids, if they goof up on these, that's where it comes from. It comes in generating this dx right here. When I replace it, I'm going to have to replace it with that fraction correction of 1 over root 2 du. So I'd write 1 over root 2 du, but we like to throw those constants out front. This is arcsine. It has a fraction correction, but then it's just arcsine urine analysis. If it's arctan, it's 1 over analysis, arctan urine analysis. So this is arcsine u over a, right? And then plus c. You could rationalize the denominator if it floats your boat. Okay, I'm not going to. Now this one looks really similar, but now look at it is Pythagorean in the denominator. But this actually, although you might go arcsine, no, this is u sub. And watch the difference. Now when u is the inside function, I now have a root u, put the dx over here, right? My du is negative 4x dx. So this x dx part, right, can get replaced by a negative 1/4 du. Done. Now it's power rule. It's negative 1/4, the antiderivative of u to the negative 1/2 du. Add 1 to the power. Divide by that power. You with me? So add 1 to the power. Divide by that power. There was a negative 1/4 out front from the fraction correction. There's a c. There's a negative 1/2 u to the 1/2 plus c. And remember, we back substitute our u choice in. So 5 minus 2x squared heading right back in here. What do you think? Pretty fun, right? All right. So let's go to the next one. Again, always go for u sub. In this scenario, we would let u be the denominator, hoping to pass off to natural log. I always start with u sub. You will. Throughout your entire calculus career, u sub's the hammer of your integration tools. It's the one we go to first and use the most often. We hope that when we take its derivative, it's a multiple or exactly the rest of the integram. This is exactly. So although You might be looking at that going 9 plus arctan. U sub's the winner here. This is in my face 1 over u du. Right? This whole e to the x dx is the du, and this is the u. That passes off to natural log, absolute value of our u choice, plus my good friend Carl the constant, not Carl Peterson. All right, now watch me make a twist on this. If we were in class, which I really miss not being able to do this, I'd say tweak it so that it does become arctan. And I'd walk around and see if anybody could do it. I'd say play with this, keep it as similar to this as you can, but make it arctan. And usually I'll see people who say, well, I won't mess with the 9 because that already has something being squared. I am going to mess with this, and they'll square it usually. And e to the x squared is e to the 2x. So a lot of times I'll see that down there so that my u can be e to the x, right? Now, if I let my u be e to the x, my du is e to the x dx. So I don't even need to mess with the top. So if you'll notice on here, I have an arctan. I have a squared plus u squared du. And it passes off to 1 over analysis arctan urine analysis plus Carl. So notice just a minor change on there made it a very, very different problem. One went natural log and one went inverse Triggy. Usually too, if you were in class, I'd say this one looks like it's a mess. I do, however, see a little bit of some arc sine going on there with that root and the minus making it ugly. Little Pythagorean difference going on there in the denominator as well, or in the radicand. So it is looking a little bit like maybe it could go arc sine, but what about that numerator? And usually I wait and nobody says anything, and then I just say if it, and then I hear the class go makes a heart, you can break it apart. So again, integration's tricky because you need to play. And sometimes, but keep in mind, I won't ever ask you to do anything we haven't done before. So if something's not working, you have to try something else we've done. What makes chapter 2 tricky is now it's not just u sub and hearts to be broken apart and letting u be the denominator to pass off to natural log. There's going to be more things. There's going to be integration by parts. There's going to be integration by partial fraction decomposition. There's going to be improper integrals. So we're just going to add to that toolbox. You're really going to have to dissect these integrals. Now, which one of these pieces of the sum passes off to arc sine? And the answer is the second piece. Bring the 2 out front, and you do have the square root of a squared minus u squared du, right? So this one right here is 2, because it's got a 2 there. Arc sine, urine, whatever's being squared, analysis, whatever's being squared, plus c. That one's done. What about this one? Usually I'll wait and someone will go u sub and I'll say yes. So this one's going to pass off to u sub, which I'm not going to review because we should be good with u sub. But notice I broke it apart. Let's go to this one. I know the notes are getting long. I apologize, but it's kind of a hard topic. So this looks maybe arc sine, but it's missing the root, right? So let's try this. Let's let u equal 9 minus w to the 4th. I think I have a typo here, simply because I think I meant to have that be a plus. All right, you'll see why. This is looking arctan, a squared, u squared, du, dw is 2w. So du is 2w dw. This does need a 1/2 fraction correction in addition to our model. for arctan. So the WdW is getting placed with 1/2 du. All right, so how do we do the arctan ones? It's fraction correction, and then it's 1 over analysis, arctan, urine, analysis, plus Carl. So 1/6 arctan, it works, it's kind of cool. I challenge you to take the derivative of this, but I wanted to keep this under 25 minutes and we're getting close. I'm not going to have you do that one. That would have been like a roll challenge. I hate not having everybody here all the time, but I do want to actually go do a challenging one here. Sometimes things that don't look inverse triggy are. I'm thinking while I make this because I've got to make sure it works. There. I think this will work. I might need to tweak the sign or two. I can't just throw any numbers down there. So keep in mind, here's what we do with integration. Do I outright know it? No. Is it set up for u sub? That's the next thing that comes into your mind. Let u be the inside function. There isn't one. Let u be the denominator. -6 plus 2x. That's certainly not a 5 dx, so I'm stuck. Well, keep in mind the only other thing you know right now is the inverse trig stuff, which means the denominator perhaps can look like a squared plus u squared, and maybe I can pass off to arctan. But in order to do that, I have to play, and I'm going to do one of your favorite things ever, which is completing the square. So in order to complete the square, we like to have it in standard form. I think these are fun. You might want to bring the 5 out front just for shits and giggles, right? Remember, when you complete the square, we're going to try to figure out what's that function that's being squared by creating one. Okay, so I'm going to leave that plus 25 out of the mix because that wasn't a perfect square. In order to make it a perfect square, you take half that middle term and you square it. But the minute I've added 9 to that denominator, I better subtract 9 because that blue stuff is what blue stuff. I can't change it, I just can give it a face look. Oh no, I'm going red. Lots of colors. So notice that denominator. You should convince yourself that this denominator right here is identical to that one. I'm just farting around with it. So I have 5 times the antiderivative of 1 over. By completing the square, I created x minus 3 quantity squared. When I combine these, I get plus 16. You'll notice this does look Pythagorean and prettier. There's no root, there's no minus. I really do think it's a squared plus u squared du. I'm just going to let that settle. So in this scenario, my a is 4. My u is x minus 3. My du is dx. So no fraction correction out front, just the 5 from the 5 in the problem. But then remember, it's 1 over analysis. Arctan urine analysis plus Carl. 5/4 arctan, x minus 3/4 plus c. We're done. And I will link worksheet 1. And this assignment covers Friday till, do it anytime as long as I get it by Sunday night at 11. I think I have the Google form set for. So because of that test, we're just kind of being a little loose here with this first assignment. Have a good one. Oh, good Lord.